Alright, let's get started. So last time we started writing this class called Vec3D, which includes a few different kinds of constructors, some operator overloading examples, and a destructor. So first, what I want to do is finish what we started in terms of the Vec3D class. And then right after, we're going to generalize Vec3D a little and actually talk about how to write a more generalized vector class. And time permitting, we might come back and revisit this vector class yet again once towards the end of the semester to look at some other cool things that we can add to it, but that's not a required part. We'll do it only if we have time left at the end. So that said, we have, this is where we started, just a quick recap. So we created a struct called Vec3D with just three components, X, Y, and Z. These are the three data members. We said we're going to just do a default constructor. Just to give an example, I did the default constructor inline, which means that we created the function and we just defined the function right there. Just to contrast, the other constructor was actually done outside of the struct, and similarly the copy constructor was also done outside the struct. So just taking a quick look at what those look like. So we did a couple of different approaches to writing our non-default constructor. One was using just different naming for the parameters, and in one case we use the same name for the parameters, in which case to disambiguate it for the compiler so that it knows which X we really mean when we say X, because it could mean this X or the data member that's X. We actually end up using the this pointer. Both of these would actually work and do the exact same thing under the hood. Just the difference is that in one case, since there's a parameter named X, we want to change the value of the object that is being passed in, we want to actually do this to the X is equal to X, so that it takes this to the X and equate it to whatever the value of this parameter is. If this X was a different name, for example, underscore X, then we did not need to do the this pointer. We could just do X is equal to underscore X, and the compiler would have realized that the X you're talking about is this to the X, and then just use underscore X from the parameter list. Again, the rule here is when the compiler sees a variable, it's going to look for, is it a local variable? If so, it's going to assume you're talking about the local variable. Otherwise, it's going to assume you're talking about the parameter. Otherwise, it's going to assume you're talking about a data member. Otherwise, it's going to assume you're talking about a global variable. If it cannot find the variable name in any four, that's when you're going to get an error. And we tried doing that by just an ill-formed name last time. The other thing we did was a copy constructor. Again, kind of a similar thing. This to the X is equal to other.x, other.y, and other.z, where other is the other vec3 object being passed that we are copying from. Worth noting that in this case, had I just said X is equal to other.x, what would the compiler take X to mean in this case? Just follow the rules. Is there a local variable called X? Is there a parameter called X for this function? So what's the third thing that comes right after? Is there a data member called X? The answer is yes. There is a data member called X. So I could have just written X is equal to other.x, and this would be the exact same thing as saying this to the other, this to the X. If I had just written X, the compiler would have assumed you're talking about the data member and added the this to the X for you. If we did not specify it, this would just work equally well. If we do specify it, it just makes it a little more explicit. But both would have actually worked. Again, to keep the hierarchy, the order in which things are checked in mind. Then the one thing we actually did was we created an overloaded operator, which is the operator square brackets, and takes only one argument, unsigned integer index. We wanted to be sure that we do not allow assert to exceed, index to exceed the value 2, because 0, 1, and 2 are the only possible indices. If 0, we want to return X. If index is 1, we want to return Y. If index is 2, we want to return Z. So we just inserted an assert in there which said index is less than vector size. Just a quick recollection that I did go through this discussion on why is, instead of putting just the number 3, it's actually a slightly better programming practice to just create a constant integer up above and just use the number 3 there, because it leaves us more room to be able to change this in the future more conveniently if we wanted to add, say, yet another dimension to the vector. It would have worked if, in fact, what the compiler is going to do, to the compiler, this is really the number 3. The vec size is the same as number 3. Why is that? Why can the compiler assume that vec size is always going to be 3? Because it's constant. It's not like the code's going to change it. So the compiler is literally just going to do a replacement. If you look at the actual assembly, you'll actually see the number 3 there. There is not going to be a variable used for vec size. But what this does is this actually puts our parameters up all the way on top, and we can just change them over here if we wanted to make a change to how the vector works. Generally, like I said again, almost always a bad idea to put a numerical literal straight in a function. There are times, like I said, almost always, there are times when it just doesn't make sense to do it any other way. For example, the number 0 here. What we're really saying is the 0th index. While I could make a constant called 0, that won't really help. It won't really add anything. It'll be like 0 is equal to 0, 1 is equal to 1, 2 is equal to 2. It won't really help. So it's not really any value doing that, because what we are going to do, the code is going to look exactly the same. So that was where we left off, where we created the operator square brackets before we left last time. So before we jump into more content today, any questions? Or any confusions from last time? All right, so I had one student actually come up and ask me a rather interesting question. Why didn't I do assert vector index is greater than or equal to 0? So one can actually argue that I could have done the exact same thing by saying vec size is greater than or equal to 0 and index is less than vector size. And then in that case, I would not have to call this an unsigned here, right? Fair point. Why did I choose to do it the other way? And so this is actually, this is exactly equivalent. It would have accomplished the same thing in terms of the code. But there is actually one very, very important difference. And one of you do know the answer, so feel free to speak out. Can anyone point out what the difference is between the assert and the unsigned? So it makes it slightly easier to debug. So what happens is if you do an unsigned here, the check that index is greater than 0, when does that check really happen? The compiler actually checks that you're not trying to pass a signed value as the index to this. If you try to do operator square bracket -3, the compiler is going to complain saying you're trying to pass in a negative value for something that's not supposed to have a sign. So you'll catch the bug at compile time. The assert is like a function call that happens when the program's actually running. If in your program somewhere you actually pass in a negative value, you will get an assertion fired at that point. It's actually preferable, and this is kind of just a big picture understanding how do I better code a more professional software. If you can catch something at compile time, it's far preferable than catching it at runtime. Here's why. So blue screens on Windows, for example, they show up. Why do they show up? Because there was a bug that was not caught until the Windows got installed on your laptop and you did something and the bug got caught at that point. Yes, the blue screen. So where does the blue screen come from? Typically, it's an assert file within the operating system. The blue screen shows up like, what do you as a user feel about the blue screen? We joke about it all the time, right? Terrible user experience. If they could have caught it before they shipped the DVD to you, would have been better. The earlier you can catch a bug, the better off you are. The worst kind of bugs are the ones that happen once the users actually have the software in their hands. Your customers have the software in their hands and they find the bug for you. That's the worst kind of bugs that you want to have. The sooner you can catch them, the better. If you can catch them at compile time, that's better than catching them during testing. If you can catch them during testing, that's better than the TA catching it for you and giving you a lower grade. It's really how the real world works. Except the TA is going to be the user of the product, your customer, who's actually going to be using it and catching it for you, usually has bigger implications than the TA catching the bug when your bugs are exposed. I believe I shared the story with you guys of a Wall Street company that actually lost about $400 million due to a software bug in about 4 hours. So software bugs can be extremely expensive and caught at the wrong time. You still catch the bug, it's just that it was caught a little too late. So that was basically just a digression worth mentioning, that if something is known to be unsigned, it's better to just call it unsigned rather than let it slide all the way until it gets caught as an assertion pop-up when your user is actually using the software. All right, so that said, any questions or anything so far? If not, then let's actually keep adding more and more functions. So we've been going in this order. The one function that I deliberately skipped last time was the destructor, which we haven't implemented yet. So let's actually do the destructor just again to emphasize that contrast, that there are two ways of writing these functions. I'm going to do that inline instead of doing it outside the struct. So we can do the destructor inline. How do you write a destructor for a class? Well, the way you write a destructor is that you actually, the way I typically do it is I just open up my constructor and I see what is the constructor doing. And if there's anything in there that I need to undo before this object can be considered destroyed and gone. Typically, all that implies is that I'm doing something in my constructor that is actually allocating memory. So either I'm calling a malloc or I'm calling new, which is a C++ flavor of malloc. If any of those are happening, that's when I want to start paying attention to the destructor. Otherwise, I mean, yes, I did x is equal to 5 in my constructor, let's say. If my constructor set a value to 5, the destructor is typically being called when the object is about to go away, which means my x, y, and z are going to go away anyways, right? This is when things are being taken off the stack, or a delete has explicitly been called by the programmer, or a global variable implies that the function is ending. Do I really care what value of x is if x is going to be gone in the next fraction of a second anyways? Because it's the destructor, that's the whole point. What I do care is if in my constructor somewhere I had something like x is equal to new int. If I actually created a new integer via, and in this case, x will need to be an integer pointer, just to be precise. If I see this line of code in my constructor, then I do care, because when the deconstructor is getting called, there's some things that the compiler is going to take care of for you. When the destructor is being called, the vec3d object it's being called for, that part is going to be taken care of by the compiler. The compiler is going to take it off. But what that means is your data members, x, y, and z, whether they were on the stack or on the heap, are going away. However, if x was actually pointing to some memory that you allocated on the heap, that's your responsibility to delete that before x, y, and z go away. So just to kind of make this, we'll just call it create an integer array called block here. If that was an integer array, I would have had to initialize it. Remember that my rule is, the way I write the constructor is I start looking at all the data members and make sure every one of them appears on the left-hand side of the equal statement once in my constructor. So block has to be initialized to something, and let's just say we call it new and say an array of 4 integers. 16 bytes of chunk allocated in a variable called block. Now, if I don't do anything in my destructor, x, y, z, and the pointer block are all going to go away, because this is why the destructor is being called. Destructor is called when vec3d is about to be deleted. So what it looks like in memory, I have a vec3d which contains x, y, z. And let's just say we just set them equal to 0 in our constructor, and that's how they stay. And then the last thing I actually have here is block. Now block is a pointer which is pointing to somewhere else in memory, a 4-byte array. When the destructor gets called, compiler will automatically take care, so the destructor again gets called if it's a global variable, that means your program's ending. If it's a local variable and destructor is called, that means the function that allocated it as a local variable is ending. And if it was on the heap, that means that somebody has explicitly called delete. But in any of those above scenarios, the actual XY, the memory allocated, let's just say 4 bytes each, the memory allocated by these guys is going to go away. But the actual pointer and the memory that was allocated by calling this new in the constructor, that's still going to stay. That's not going away anywhere. Because only this part goes away. The compiler, when the object is deallocated, the compiler does not go inside and look for pointers and see if those pointers are pointing to something else that was actually allocated. The compiler is just going to take these 16 bytes off of either the stack or the heap or the global variable space, depending on wherever it was, and it's just going to forget about it. So it's up to us to make sure that any memory that we allocate during the constructor does get deallocated. So in this case, I kind of artificially went ahead and added some memory allocation, which means that we actually ought to be deleting this memory and to be precise, I should use the delete array operator. So delete array block would actually get rid of, would actually take care of this. Now, while we are at it, let's look at the other scenario. If block did not exist, I could actually leave my destructor completely empty. It didn't have to do anything because there was no memory being allocated in the constructor. Hence, I don't need to deallocate anything in the destructor either. If there is memory being allocated, then you actually delete it. So it's worth remembering that you can have a completely empty destructor, and that's perfectly fine. There's nothing wrong with that. If there's nothing to be undone, there's nothing to be undone. You can just leave an empty destructor. Does it make sense? All right. Yeah.
The variables, you're not allocating any memory to them, right?
What's that?
Sorry, the integers, you're not allocating any memory to
the
them.
X, Y, and Z, you mean?
Yeah.
Yeah, so X, Y, and Z are getting memory because everything needs to be stored somewhere in memory. But the fact that the destructor is being called already tells you that the compiler is about to call free on the vec3d or take it off the stack or delete it because the program is ending depending on where it was. Again, that mapping that I keep saying, keep that in mind. If you're on the stack, then it's going to be, that means it's a local variable, and that means the function's ending. So the only reason you are in the destructor is because that object, this piece, is about to go away. Wherever it is, you don't care. In the destructor, you don't care where this piece is. What's important is, did I actually allocate memory to it in my constructor? And if I did, I have to remember to deallocate. Otherwise, I'll keep creating vec3d objects, and I'll keep creating these arrays and never deleting them, eventually running out of memory. And we have all seen out how the heap works and how that actually happens. So anything you put on the heap during the constructor, you have to make sure you take it back off during the destructor. Does it make sense? So typically, most of your destructors will have nothing but a couple of delete statements, 1 or 2, or 0 or more than 0 delete statements. That's a very typical destructor. That's what it looks like. All right, so let's keep going. We have looked at the index operator. Now let's actually go ahead and write a couple of more operators. Say the plus operator. So we'll just do it outside, just again to contrast. So operator plus vec3d and other. So in this case, what we want to do is return a new vector. Return a new vector which basically contains the contents of the element-wise addition of this and other. So it's going to be something like, just going to create a vector called temp.x is equal to this to the x plus other.x. temp dot y is equal to this to the y plus other dot y, and then temp so let's talk about this since it's interesting what why the compiler is actually complaining. You can clearly see that the compiler is complaining something about this not being there. Can anyone see why the compiler is complaining about this when it didn't complain about it in any of our other functions? Yeah.
You didn't specify that that was for the vec3d.
I did not specify that this is actually a member function of vec3d. How do I specify that? The colon syntax, exactly. When we do that, it's good to go. This is now available as an implicit parameter. So this is only passed when we actually have so this is only passed when we actually have the what you call the colon syntax specified up front. I actually want to do a couple more. So I want to do, let me remove, let's just do that actually. Let's just get rid of this guy. So then the other thing is we do vec3d operator plus and notice that it's the exact same function name, vec3d colon operator plus, but this is where we are taking advantage of the signature matching that C++ does for you. So we are creating another operator plus, but this operator plus actually passes an integer as the argument, and the compiler is smart enough to actually pick this one up. So what we're going to do is we'll do vec3d temp, and then temp.x is equal to this to the x plus k. Temp.y is equal to this to the y plus k. And then temp.z is equal to this to the z plus k. So just adding k to all the elements. And then we're just going to do a return temp. So we've basically gotten so two operator plus, but automatically this one's gonna be used when the other side is the integer, and in this case the other side is the vector. So worth mentioning here, by the way, that this will work when we have clearly a vec3d plus a vec3d, and this is what's gonna get executed when we have vec3d plus k, an integer basically. When it's not going to work, and this is equally important to mention, is when we do int plus vec3d. It's actually not going to work in the latter case. Why is that? Because compiler goes from left to right. The compiler is going to recognize that we have a vec3d. It's going to see a plus. It's going to see an integer on the other side. It's actually going to look for operator plus defined inside the class vec3d or struct vec3d, which takes integer as an argument and actually just go ahead and use this function. If we do it the other way, it's going to do the same thing. It's going to see integer, it's going to see a plus, and then it's going to see that integer does not have a plus with vec3d defined. So it's just going to come back with, I don't know what to do with it. It's not going to work. So that's pretty much it. I mean, we've gone through and defined our vec3d class and taken a couple of different approaches at this point. The file, let's actually call it, for some reason it was named header.h. Let's see if I can rename it easily. Looks like I can. So now we have a file called vec3d.h, which contains the struct and the function definitions of this. Now there's actually a slightly better way of doing this. Again, goes back to coding style. It does not change, but it's a slightly better coding style that functions that you do not define inline, the ones that I have here, for example, it's actually better practice to put these functions in a CPP file rather than in a header file. So, and you'll see code both ways. So typically when you're doing it inline, you don't even have a choice. You have a header file, functions are defined right within inline. There's only one header file that goes around everywhere. When we are doing something like this, we have a choice. I can do everything the way I've done right now. I did it this way only because I wanted to kind of have the ability to scroll back and forth conveniently between the function declarations and their definitions. But the better practice would actually be to actually create a CPP file and change and move these function definitions into that CPP file. So while we are at it, let's go ahead and do that. It's usually the practice is to call that CPP file the exact same name as the header file. So we'll do vec3d.cpp. So now we have a vec3d.h, the header file, and then vec3d.cpp, which is clearly empty at this point. So what I'm going to do is just cut all of this from here and just drop it into the CPP file so that we get a cleaner picture. So now we have a header file that actually declares the functions. Notice now everything that was vec3d went red underneath. The reason is that we actually need to include our file vec3d.h here. When you include the header file, now it knows what vec3d is, and all the reds disappear. And just to be dead sure, you can go to the other side and notice that the green lines disappeared as well, because it knows that the functions are being defined, they're just being defined in a separate file. Make sense? Just a quick thing. And because this is how you're going to see it in your programming labs, and I want to walk through why we do it this way.
Professor?
Yeah.
Why are we having two?
Why do we do two files?
Yeah.
So it's actually a better programming practice to do the definitions and the declarations separately when you're defining your own classes. There's more advanced reasons why we do that. There's other topics that we won't get to in this class around inheritance and how we can actually take these different structs and actually tie them together. Having a header file does actually come in really handy. Another reason that it comes in really handy, by the way, is separating it. And this comes across a lot when you're dealing with, say, we are not coding anything with Windows, or if you're coding with Android or iOS directly. So Apple wants you to write an application for their device. Obviously, that's how they're making a lot of their money. In fact, for those of you who don't know, Apple makes more money selling apps than they do selling iPhones. So that's why the iPhone prices have dropped so much since when they started 8 years ago. What actually is, so they clearly want to incentivize people to write apps. They want to make as many libraries and convenience things available to you. So for example, if you actually try to write an iOS application for Apple, ever notice that there's a stark similarity between a lot of the apps that actually exist out there? Pretty much when you go to the menu items, almost everything looks the same, it opens up the same way, drop-down menus look about the same, regardless of Facebook or LinkedIn or whatever company's app you're dealing with. It's not a sheer coincidence. The reason that it happens that way is because Apple actually makes all of those elements available to you so that you just say, I want a drop-down list and I want these 10 things to be in there, and the drop-down list gets created for you. You don't actually have to write the code for making the pixels appear on the screen and making them disappear when someone unchecks. Why does Apple do that? Obviously to make it easy. So more people write apps. As I said, more people who write apps, more money Apple makes. That's really how the equation works. Now Apple's all incentivized to write all these convenience things about lists and buttons and how to do this to provide as many classes, as many structs as it can with all these things embedded inside. At the same time, Apple has a conflicting goal, which is Apple does not want to make all their source code of how they write their lists available to the general public. Because who's the first person that's actually going to take and run away with it? The Android guys. And again, just a little bit of history there. The way Apple does their icons on their home screen actually caused a huge lawsuit between Samsung and Apple a couple of years ago. And Samsung ended up paying a couple of $100 million to Apple for that. So Apple wants to show you Apple wants you to use that list, but not want you to tell you how to do that list. It's a pretty genuine use case, actually. Apple's not the first company to do that. Windows is all over the place. I mean, starting similarity between Windows applications, right? It's not a coincidence that every Windows app you open has a file menu at the top left, exactly in the same place. That's because Windows makes a tool, a struct available where you just call the constructor and it constructs that file menu at the top of your screen. You don't have to know how to get those file menus getting up there yourself. All of those use cases kind of speak to something, which is I want people to be able to see what functions they have available and what the data members and everything looks like. I don't want them to have the ability to see what the contents of the functions are. I don't want them to know how I do that fancy looking drop-down menu when you press on an Apple button, because I don't want Google figuring out my algorithm. So how do you accomplish that? You create your header files and the CPP files separately. You give the header files and put them out in the open public. Anyone can read the header file. Anyone can see that vec3d contains a function called operator square brackets. At the same time, somebody looking at this just knows that this function exists, has no idea how it's implemented from the inside. That's our business. We took care of it in the CPP file, right? So this is how most code is actually distributed in the world, where you keep the CPP files, you compile them, and you keep them to yourself. You make them part of your Windows or your Apple, install it on Apple, and don't make them available. But you make the header files open to the world so people can see how they can use your struct, but they can't see how they can use your function, how your functions are actually done, so they can't cheat off of you. So that's kind of the real answer is when you get to real professional coding and writing code that is actually distributed, which is the real world, you actually want to do it this way so that somebody can use my code, but not, somebody can use the convenience thingies that I have written for them. Remember, this kind of goes back to that whole Facebook lecture about tying objects together. We have now created a vec3d object, which is pretty convenient. Anyone who wants to do a three-dimensional vector in C++ can just use our vector. We just don't want them to know how we actually did everything, because that's our intellectual property. We don't want them to know our algorithms. So what you do is you give them the header file, you don't give them the CPP file. So that's usually the biggest incentive for separating header files and CPP files. For libraries that are intended to be open, for example, the standard template library in C++, which actually has a lot of convenience features, actually there are no CPP files in that library. They just put everything straight inline in the header file, because they don't care. It's supposed to be open to the world anyways. It's just written by the people for the people. So, but yeah, so for most cases, for this reason, people like to separate the stencil or the layout that we put together in the struct, and then want to keep it separate from the actual implementation of the functions.
Professor, if I create a library and if I want people to use it, so on their own system, for example, I created and put it on Git.
That's right.
So will I just put up a header file for them to download and use it, or do I
Yeah, so you have to give them the header file and either give them the CPP file, or when the compiler runs, the compiler takes the CPP file and converts it into a binary file. So what people typically do is just give them, so on my iPhone, I do not have, say, vibrate.cpp for the vibrate that actually runs on my phone. I do have a vibrate.h, which tells me how to actually work with the vibrate function. The vibrate.cpp file was replaced with a vibrate.o. It's a header, it's a binary file which is just sitting on my phone that actually interacts with that functionality on the phone.
There's no way you could decode that binary file.
I mean, no way is a really strong word. People have been doing it for ages, actually. On how, I mean, this is how software gets hacked. People are able to take binaries and reverse engineer what it's actually doing. Because binary still means it's still x86 assembly. Zeros and ones, it's a pain to figure out what it means. Go back to your 306 days, right? Think about those zeros and ones, the first programming lab you did in 306. If someone gave you a bunch of zeros and ones and said, figure out what this program does for LC3, it's doable, it's just a pain to do it. Try doing it with 5 million lines of zeros and ones, it's a significantly harder problem to solve. Still doable. So that's a risk that these companies do take. This is exactly where that lawsuit between Apple and Samsung comes from. Apple basically accused Samsung that they took the binary files and tried to reverse engineer how the algorithm was implemented and did it themselves in their phones. And eventually they found enough proof that it was actually the case, so Samsung had to pay out.
So you make the header file and the binary file available, right?
Yeah, that's the best way to distribute software. All right, so that said, so this is why if you were ever curious, most of your programming labs that you deal with, we always have CPPs and header files separated. That's where the best practice really emerges from. All right, so we have a CPP file now called vec.cpp. All good to go here. The next thing is this one very important thing that this is really everything that we have done so far. I would say we have created a library for vec3d. Now let's actually write a small program that actually takes advantage of this so that we can actually test if our library really works. So I'm just going to create yet another CPP file. We'll call this one, we'll just leave it as source.cpp, the default name. So source.cpp, one of the first things it needs to do is for us to actually do anything useful with it, that we are going to have to include vec3d.h so that we can actually take advantage of what's in vec3d.h. The next thing we're going to do is we're going to just write a main function. And I have a suspicion that we are going to end up using some print statement, so I'm just going to go ahead and add stdio anyways. So we have the main function now. We can do vec3d and actually declare a vector. Let's call it v1. And notice how the compiler did not complain. It's actually figured out that you're talking about vec3d, and we're able to declare a new element. Let's actually do another one. So first things, let's actually start with just this, make sure everything compiles, because that's always a good idea. So let's see how our compiler runs. Okay, so no errors, everything went through. Let's put a breakpoint here and just run it one more time. All right, so we have a breakpoint here. Notice that right now, and for those of you at the back, I know you can't see, but x, y, and z just have a bunch of random values, large negative values. What do we expect to happen next? v1 has been created on the stack, but what's the immediate next thing that's going to happen? The constructor is going to call. Which constructor is going to get called? The default constructor. So if we go a step into, as expected, it landed straight at the default constructor. Our default constructor is going to run, and our x, y, and z are now going to become all zeros. Block is going to get its own memory. And again, we can just hit continue really at this point. So continue. And just goes through. With a vector being defined. So this is v1. Now let's actually do a second vector v2. In this case, let's actually do something slightly different. So we created v2 with 3 values, 1, 2, 3. What constructor do we expect to get called in this case? The non-default, the one that takes in 3 values. And then we can actually do vec3d v3. And this actually takes in v2 as the argument. So that's what's going to lead to the call for a copy constructor. We have the 3 vectors available. Let's do a couple of other things. We can actually also do vec3d v4. And we'll just do v4 is equal to v2 plus v3. Now let's actually try a few other things. So let's say we did v4 is equal to, if instead of that I did v4 is equal to v2 plus the number 3. That looks like fine. Let's actually try 3 plus v2, and you can see right away the plus actually got highlighted, and it says no operator plus matches these operands, int plus vec3d. That's exactly what we expected it to be. Now, there's one confusion that I've seen students have in the past, so I want to stress that right away. This does not imply that somehow the definition of plus in C++ has changed globally. All it implies is that whenever you'll see a vector as on the left-hand side of a plus sign, it's going to look for an overloaded operator and use one appropriately. So just to nail it, if I did int x is equal to 2 plus 4, this is still going to work. There is no problem here because the plus symbol still is the plus symbol. Yes?
Is it possible to so for example int, is it possible to add operator
Yeah, so the question is it possible to add the operator? Let's not get into that right now. If time allows, at the end of the lecture, we'll come back to it. So the answer is it is possible. You just have to so int is not a struct, as we know. So it's actually not going to be a member function, but there is actually a way to overload it. So there's one more concept that I definitely want to get to. Once I do that, I'll come back to this. So just ask me that again in about 25 minutes. Okay. So we have the vector, we have looked at the constructors, the different constructors being called, we have looked at the plus symbol. I think there's one more thing that I definitely want to test here, which is, can we actually do, say, v2 of 0? Because remember we overloaded that plus the operator. So what I'm going to do is, and then just for brevity, I guess we can actually do one more. X is equal to 1. All right. So let's see if we can actually get this one through. We'll just go ahead and drop in a few of these guys here. So want to see a stop point here. I want to definitely see a stop right here. Okay, let's run. Right, so everything goes through. For those who can't see, this is actually pretty interesting, in fact, to know what's actually happening here. You definitely see more lines than expected, in a way that there is V1, V2, V3, V4 all down here already, with X, Y, and Z just having extremely large random values, -858, 99, 3460, and then there's more dots in front of it. So your local variables have been put on the stack. That's why they're being shown down here. What hasn't happened yet though? Why are the values so funky? The constructors have not been called yet. So the constructors are going to get called as we go literally one line at a time here. So instead of step into, I'm just going to do step over. The first line, notice it turned red. X, Y, and Z are now all zeros. The second line, it turned red for V2, and X is equal to 1, Y is equal to 2, Z is equal to 3. That's how it was set up. When we do a step over the third line, V3 now contains the exact same values for X, Y, and Z as V2 did, as expected. And V4 became 0, 0, and 0. That's because the default constructor for V4 was called. So everything kind of working as expected. Now it's kind of getting interesting. So we are about to do V4 is equal to V2 plus V3. V2 is X is equal to 1, Y is equal to 2, Z is equal to 3, and V3 is also 1, 2, 3. So we should expect to see 2, 4, and 6 as the 3 values. Let's just go ahead and step into this guy. So we got in here, we'll just do step into, and notice what happened here. It was temp that was being declared, right? Temp means that it actually got into the default constructor for temp. So temp's now going to get the 0, 0, 0, and really didn't want this, but that's fine. We are back here. And so all set with temp. Temp got 2, 4, and 6 in X, Y, Z. And now we're going to just do a return for temp all the way back here. And we actually got an error thrown. It's actually talking about some kind of an access violation that happened here. What's that? So this was something we talked about last time. Anyone want to venture a guess on what happened here?
It's reading memory, it's not allowed to read.
Yeah, so that's the first thing. It's reading memory that it's not allowed to read. So let's do this again. Let's actually go through it, what happened here step by step. Remove this. Let's remove this. So v2 plus v3, v4 is equal to v2 plus v3. That's where our problem occurred. We're going to put a breakpoint right here at v4 is equal to v2 plus v3. And let's actually stop debugging and start it again. Just make sure the error comes up. Right? So the error is actually popping right here when the destructor is being called. What is the destructor being called for? What variable is the destructor being called for? Well, a level above it. What is actually happening in here? Why is it destruct? We are actually trying to destroy temp at this point. And as soon as it actually tried to destroy temp, we actually got an error. Anyone want to venture a guess on what happened here?
Temp is going to be destroyed anyway.
So there's something that I made a terrible mistake here actually, which is, and I did this for educational purposes. Clearly it wasn't needed. Block, as we all know, is kind of off. So delete int4, setting this up, and then there's delete array for block right here. How many different constructors exist actually in this struct? There's 2 constructors. Actually, there's 3. This third one is a copy constructor, right? Is the block actually being taken care of in all situations?
No.
Even worse, when I'm doing a copy constructor, am I copying the block over correctly? I'm actually not even bothering to copy it when I'm copying the copy constructor. Remember, we just copied x is equal and y is equal and z is equal to that. So this is going to, what ended up happening is, my copy, I have a random value in block because a copy was made. And remember the copy, why did the copy get made, by the way? When is the copy constructor invoked?
When the only parameter is another vector.
Copy constructor gets invoked when you pass something in or you try to return something from a function, because that's when a copy of a variable happens. Remember the whole thing about pass by copy? So what it's trying to do was, what it was actually trying to do, make a copy of temp so that it could pass it out. It made the copy, the block did not have, the block value did not get copied because we had a bug in our copy constructor. And when you try to call delete on an invalid pointer, that's exactly the error you can expect, which is I'm getting something that does not work. If we actually go ahead and remove this, which is the way it should be, the error should go away. Does it make sense? So, lesson learned. What's the key thing that you want to remember? What's the problem here? What rule did I violate that I set for myself when we started talking about C++ last week? How do you write a constructor? How do you start writing a constructor? We've talked about it a few times. You look at your data members and you make sure each one of them is initialized, right? What happens if you go and add a new data member? What should you be doing? Make sure that you go to each of your constructors and make sure that the data member is also initialized. If you add a data member without thinking, and I have a story to share on this, I think probably one of the most interesting stories. This was my internship at AMD back like 11 years ago. And we actually had a C++ class. I actually made this exact mistake. I added a data member it was luckily in this case it was memory and it got caught. What if it was not allocating anything with memory? We would not have caught that data member. It was not being initialized in 2 of the 3 constructors, right? What that meant is that code would have worked every time the first constructor was called and not worked the other 2 times. So I actually had an uninitialized global variable. It was a massive research project I was doing for AMD. Had an uninitialized data member, which was not being initialized in one of the constructors. What that led to was, there was a random variable in the middle that would actually get added to a lot of other things. There was no way any assertion or anything was going to fire from that, because it was actually a data member where we were collecting statistics. So it was just being added to it, was not being passed around much. We actually ended up with completely wrong research study results, wasted about an entire month on those results trying to explain them. And at the end of the month, it turned out the results didn't make any sense to begin with because one of the constructors was missing initialization for that variable. So, and this is how mistakes happen. So when you actually are just like when we went with the constructor, make sure that your variables are initialized. When you have a data member, and you add a data member later, make sure you go and update all your constructors as well. That was a mistake I made here. I went half on this and didn't go full way. The right answer was to remove it, because this is just really an example and was just polluting our class to begin with.
Is an int block already defined as a data member?
Yeah, it's defined as a data member, but it's not initialized, right? It's going to start out as a random value. It's not something that is going to have a value. What we need to do is we need to initialize it. It's declared. So sorry, correcting your terminology. It's not initialized. Int start block is a declaration. All it means is it's given 4 bytes on the stack or on the heap, depending on where vec3d is. We have all seen the values start out completely random. It's just, and in fact, notice what exactly is the value. So in fact, you don't even have to take my word for it. We know that this is exactly where the crash happened in the delete. I just opened up the contents of the struct. The content of the struct being pointed to by this, exactly what we expect to be, because this is the pointer being passed to your destructor. Notice the values. The x, y, and z are 2, 4, and 6, exactly what we want them to be for temp. Notice the value of block, a whole bunch of C's, not a valid pointer. And this is because temp was not initialized. The copy constructor was not actually initializing block correctly. So let's go back and do the same thing again, but this time with fewer bugs. Went through smoothly. We did not get any errors, got to the same line, and notice that v4 now does actually have the correct value. X is equal to 2, y is equal to 4, z is equal to 6. Make sense? The other things that we want to do is the next thing we want to do is take v4 and equal it to v2 plus 3, which should do an element-wise plus, which means v4 should get v2 plus 3, which means 1 plus 3, 4, 2 plus 3, 5, 3 plus 3, 6. 4, 5, 6 is what we expected it to be v4, and it is the case. Just as a next step, v2 element 0, what do we expect it to be? It should be 1. And let's look at our console to make sure. X is equal to 1 got printed. X, we should expect to see x is equal to 2 getting printed at this point. Y is equal to 2 getting printed, and that's exactly what printed. And then just for the heck of it, like I said, the integer add still works. It does not mean that now the computer is broken and it can't do anything useful. Because I did get a lot of questions back in spring. People started asking, like, how can I undo my override because my plus doesn't work anymore. The plus continues to work. It's just so that's basically all the concepts that we have talked about in class in a nutshell with C++. How do you actually have a struct? How do you do operator overloading, constructors, destructors, signature matching, and just everything set together. Any questions? All right, so there is a data structure in C. This is our vec3d Mickey Mouse example that we did for the class. There is a data structure in C++, or typically associated with C++. The data structure is independent of the language clearly, but it came into existence around C++ and was not there in C. Also called vector, and it's almost like an overload. The only difference is, notice that there's no 3D here. What the vector is it's basically an n-dimensional vector. It's a vector that you can make as big as you want and as small as you want. The best use case for the vector is, it's really a smart array. That's how people think about it typically. So let's start with, I said smart array. So what's dumb about the array? And we've talked about some of these already in class at different times. So what are the things that are wrong with the array? Can someone kind of go down the memory lane quickly and pull out some of those?
Can't change size.
You can't change size, that's right.
That will stop you from writing outside of it.
That's right. There's no bound index, there's no index checking, basically. There's no assertions in there. Any other ones? Yeah.
No easy delete. Like you have to copy over every. You know, ship the entire. Alright.
So no easy insert is what you're saying, I think. Insert or delete both have the same problem. So I will need to be on the left side of the text for me to have a legible handwriting. So any other? Any other ones? This is a good enough list actually.
Professor, one more thing.
Yeah.
Why exactly do arrays start from 0? Why can't they just start from 1? And I mean, it would make life so much more easier.
It's just a convention thing. That's just how it needs to be. In fact, not all programming languages even start with 0. But most programming languages do start it with 0.
If size is 5, you'll possibly want it from
1, 2, 3, 4, 5. But that's just a convention thing. When we think in terms of binary, we generally think everything starts at 0. So that's really where it came from. In fact, I get accused for doing that a lot. Like, typically when you're breaking things down or breaking tasks down, like I've mentioned this to some of you in the past. As a consultant, one of the things that I do for people is just go and help them break their projects down in a way that it's actually doable. And I'm accused of doing this a lot because when I start creating phases, most people start with phase 1 of the project, phase 2 of the project, phase 3 of the project. I almost always start with phase 0, phase 1, phase 2, phase 3. So it's just when you get too much into binary, that's how 0 is where your life begins. So, okay, so that said, it actually so there's 3 parts here. What we can actually do in C++ is, remember that we don't have to play by the rules anymore because we can actually override the index operators. We can actually create a thing called a smart array, which often is referred to as a vector. It has all the goodness of the array, which means you can index it and you can just create one. But it also provides some additional functionality on top using operator overloading and some additional functions that can actually take care of your insertions and deletions, index check, the ability to change size and create a resize function. So how we do something like that is we typically just create a new struct called struct vector. And what I'll do is I'll actually post an example vector implementation for you guys to play with. It's typically very simple. So what is the first thing that exists as a data member in an array? Actually, let's not do it on the board. Let's just do it right here. It'll be more useful if we just did it here. So stop debugging. Source file. I will just create a new source file called vector.h. So we're going to call a thing called struct vector. For us to be able to have an array which does not have these problems, let's think about what the data members for the vector need to look like. There's still going to be an array somewhere because the data has to be saved. There's going to be some memory. Let's actually call that the elements. So I'm just going to say int star elements, very similar to our set example. What are some of the other data members that make sense to have for an array? Size, because this is one of the things that we want to do is A, change size, and B, be able to check if the index is in bounds or not. So we want to keep size around, right? And that's actually what you need to begin with to start writing a smart array is you just need a place to put the elements because there's going to be a data place, a place to put data and size. Let's actually start writing some of the constructors here. So the default, I'm going to do it all inline just so we don't have to flip between 2 files and scroll up and down. So vector, this is the default constructor. Remember that the first thing you always want to do is you want to make sure that you don't miss any data members, especially after what we saw happen to us earlier. This is the default constructor. As a default, there's a couple of options. We can either say this is a default constructor and array size is not being passed to us. So we can just start with size 0. That's one way of doing it. So we're just going to say elements is a null. There is no, I guess null doesn't seem to be defined here, so we'll just do a 0. So both elements have been defined. Now let's actually start writing some other useful functions. It's an integer array, so I'm just going to say, well, if it's an array, it better have an index operator, right? Unsigned int index. And that is, what is that function going to look like, in fact? First, let's do the easy case. Elements is an array pointer. So if I just do this, will this work? It's just one line of returning, taking something from the elements and just returning it. Can we make it smarter?
Yeah. We have to check if index is within the size.
Exactly. We have to check if index is within the size. So we can do the same thing we did last time, which is index is less than size. And as soon as I do that, I can just do. Okay, so that's one thing that we can do with an array. Yep.
Just like a quick thing about assert. What happens if it's not true?
It's just passed. If it's not true, then the program crashes. Remember the pop-up we were seeing earlier when we were trying to access memory out of bounds when we had that bug in temp?
Oh, okay.
That's basically what it does. It just brings up a pop-up. Yeah.
It still always crashes at runtime. Like,
Yeah. So this one will this one will crash at runtime if index is greater than size. And what the compiler will do is if it sees, like, if you try to pass in -3, somehow trick the compiler into letting it go, which it is a way to do it because we've all seen how you can do typecast. So you can take a negative value and typecast it to an unsigned integer and actually pass it in. However, what is the negative value when you typecast it to a positive unsigned integer? It becomes a really large value. Like a -1 becomes 4 billion basically. So that's what's going to happen. It's going to fail this and say index is 4 billion and not less than the size.
so if you did assert 5 is smaller than 1, it would still fail like even though you put in numbers.
If 5 is less than 1, that's right. Yeah, that's right. It's going to fail. Asserts are only going to fail at runtime. That's right. Okay, so that's useful. We already took care of one of our worries. The index check's gone. That one's taken care of. No easy way to insert or delete, right? So let's start with the insert since that's the easier of the two. So typically what we do for the vector is we actually view the array as sort of like a data structure that has elements. You can push stuff at the back of the vector. We call it a push back function. That means add something to the end of the vector. Make sense? So push back, it's going to take int k as the argument. Remember the other argument is going to be this. What is this going to look like? If elements, I'm checking basically if elements is not equal to 0, because if elements is not equal to 0, and you'll see how this looks different in a moment. So let's start with the easier case first. Let's say if elements is equal to 0, what does that mean? If elements is equal to 0, that means it's pointing to nothing right now. In which case we want to create a new array. So we want it to be elements is equal to new int. I'm just going to say an array of size 1, just to keep it consistent with everything else. So I've just created an array of size 1. And then what do I want to do? I want to do elements of 0 is equal to k. That's how I would get my first element in there. Now, but is it now, what happens if somebody calls this again on a vector? Now there is something in there, right? So what I have to do is else. And this is where it kind of gets interesting. So this is the main thing, the main reason we were going through this exercise was, so far we've done it with like length as the only element. What this means is, what is it that we are going to have to do? We have an array of size 1. Now we want to insert something else. What is it that we're going to have to do? We'll have to go back and declare a new array of size 2, right? Copy this guy over, insert the new element here, And that's when the pushback's going to be done. And then we have to make sure that we go and delete this. So step 1, create this. Step 2, create the copy. Step 3, do the insert. Step 4, do the delete. Right? Going to memory, creating new memory, deleting. So if the array has 10 elements, every single time I'm going to be creating new memory and deleting old memory. Too many times, very slow to run. So there's a technique that we call amortized doubling. Amortized doubling. And this is kind of the crux of vector, actually. So what you do is, with amortized doubling, you never declare as much memory as you need right away. You always declare a lot more memory than that. So what you do is, let's say we have one element right now, and let's say the value is just 1. I get an insert. I just go to 2 elements like we were doing last time. Exact same steps. Copy this over, delete this guy. Now I have 2 elements, say 1 and 2, right? Now let's say another insert comes in for the number 3. In the old mechanism, what would I have done? I would have gone now, deleted this 2, created another one for 3, and then just kept going. So in the old way of doing things, it would have grown something like this. New 1, 2, and 3. That would have mean delete this, create new memory, copy everything over. So in the new scheme with amortized doubling, the idea is that you never increase the size by 1. You always just double the size. That's where the word doubling comes from. So you copy the 1 over, you copy the 2 over, you move the 3 in. But notice that now you have an empty slot left here, right? So now next time someone comes in with an insert 4, you don't need to allocate new memory. You'll just be able to drop 4 in right here.
But you still have to delete the previous ones, right?
Yeah, in this case, yeah, you still have to, you have deleted this, you have deleted this. But when 4 comes in, I don't have to do yet another transformation. I can just drop 4 in here. Make sense? Now when 5 comes in, I have to go through the exercise again and go 1, 2, 3, 4, 5. And then, but now I get 3 empty slots for 6, 7, and 8. I keep doubling it every time. Obviously, when you get to like 1,000, for example, now you double it, you go 2,000, so you get 999 empty slots. So your insertions, the concept is you double every time, and it's amortized in that I pay the price once for doubling, but then for the next, say, 1,000 inserts, I get cheap inserts. Then I pay the price once to double everything, and then for the next 2,000 of them, I'll actually get cheap inserts.
Yeah. Any reason why we're doubling and not tripling? I know it sounds.
There is actually no reason for that. It's just doubling. It just tends to work. You could do tripling, quadrupling, whatever you want. The crux of the idea is that I allocate more memory than I need, and then copy everything over. Thanks. I allocate more memory than I need, just copy over because it makes. That's where the term amortized comes from. That over a longer period of time, my pushbacks becomes cheaper and easier. But I pay the price all at once of copying everything. Does it make sense? So we'll spend a little more time on this on Monday, but that's basically the one concept that you guys did not have. Pretty much, we've covered everything else around C++.